Welcome to our next video for Stat 212. In this video, we're going to talk about just the basics of model selection. And I say the basics because there is a whole lot that could be talked about on this topic. There is, multiple classes that you could take on statistical modeling and model fitting and model selection. And so we're just going to be talking about a couple principles in this course. But just so you kind of have some ideas, when you're thinking about model selection, you can transform variables. You can add polynomial terms. You can transform the response variable. You can build what are called interaction terms, where predictors might actually interact with one another, as opposed to just everything being strictly solo predicting the response variable. You get into a lot of different opportunities for how you can fit a model and how we can use different criteria to decide what model is good. It's also a very contextual topic, meaning that fitting a model also kind of depends on having good theory about why variables should relate the way they do. So there's just a whole lot to talk about, and we're only going to talk about a couple things that hopefully give you a sense of what model fitting is about. So one principle that I think is important, it's not always a priority, but in many cases it's a good priority, and that is building what we call a parsimonious model. And this word parsimonious means not to spend all you have. It means to be very frugal about what you're spending. And we use that in terms of model selection because we don't necessarily want to use all the predictors that we can think of and put them in a model. And one reason might just be because predictor variables can be expensive in real life to collect. They can be difficult to get well. They can cost a lot of time. And they also just, can make your model a lot harder to understand if you have a whole lot of terms in the model to begin with. So there's a lot of reasons why, in many contexts, I would rather have a simpler model when possible, as opposed to trying to throw everything that I have in. But again, that kind of depends on context and needs. If your goal is purely prediction and you don't necessarily want to understand how the relationships work, you just want to get really, really accurate predictions, there's a case for including, lots of predictors. There's a case to be made about actually having a very complex model in that case. But in a lot of situations, parsimonious is good. If we can do that, it's often a valued characteristic of a good model. So adjusted R squared, again, is a very simple measure that we can use to help us decide if we should add a predictor or not. There are other ways that we can decide this as well. So we can talk about, or we could talk about F-tests for comparing models to see if a more complex model is adding a statistically significant amount of variability explained. We don't really do that in this class. So we're just going to kind of use adjusted R squared as our very rough measure of, is this model better by adding another predictor? So obviously if adjusted R squared goes down, we probably shouldn't add a new predictor. That's probably doing worse than random chance. It's probably not adding anything concrete to our model. Even if adjusted R squared goes up by a small amount, we don't necessarily keep it because it just depends on, well, is it explaining enough that we think it's worth it? So one really, really general criteria that we'll use is kind of this 1/20th rule, that if adjusted R squared only increases by less than 1/20th of the remaining variability, the remaining unexplained variability, we should question if it's really adding enough to our model. And so I just kind of mentioned that not because this means something, not because there's anything magical about this threshold, as much as it's just kind of a good thing to keep in the back of your head. It's not just that it goes up, but that it should go up by a meaningful amount. And if it doesn't go up by a meaningful amount, we should really question if it's worth including in the model. Is it really, is it really helping enough that we'd like to include that additional predictor? Another way that we can kind of think about model selection is that it's kind of like putting a team together, where it's a team that we want to either work together or kind of balance different strengths. So we talked about multicollinearity on the previous page, and multicollinearity is this idea that multiple predictors might be explaining a lot of the same variability in the response variable. So that's kind of like fitting, I guess, I don't know what sports people know. I'm going to go with baseball because maybe people know that. Like I'm not going to put a team of pitchers on the field, right? I only need one pitcher, so I'm not going to put 5 pitchers on the field at the same time because that's kind of redundant. Instead, I want somebody who's good at pitching. I want somebody who's good in the outfield. I want somebody who's good catching at the plate, right? There's different roles, and I want people who together can explain a lot of variability in the response variable. I guess that analogy I just completely pivoted there in the middle of the analogy back to regression there. But it's the same idea, right? So when you think about picking predictors, we want predictors that explain different parts of the variability in the response rather than just necessarily the top solo predictors, because the top solo predictors might end up being very collinear with one another, and thus explaining a lot of the same variability. So we want to be choosy about picking different types of predictors that explain different types of variability in the response variable. So I mentioned this before, but there's selection methods that you could read about and learn about if you're going to be doing model fitting one day, such as forwards and backwards selection using criteria like AIC or BIC. There's also something called cross-validation, which helps you determine if your model fits well and predicts well on a new set of data that wasn't used to fit the model to begin with. Things that are, again, a little bit beyond our course, but things I'm just going to kind of put in your head there in case you do more of this or do some self-learning on your own. All right. So with that in mind, let's go ahead and look at an example here. Consider the following models to predict an individual's weight using these different predictor variables. And it looks like we have 3 predictor variables available to us. We have arm, waist, and height of an individual as 3 variables that we can use to help predict someone's weight. And so I notice here, number 1, that I have done every combination of predictors that I could do. So for example, height as a solo predictor of weight, waist as a solo predictor of weight, arm as a solo predictor of weight. And I can see how much variability in weight I seem to explain in each of those different situations. I can also see what happens if I combine any 2 of these predictors, so height and waist, arm and height, arm and waist, and I can see how much variability I'm explaining. And then I can also compare that to what happens if I use all 3 criteria together. So the first question here is, which of these models is technically the strongest? Which model is technically explaining the most variability in weight? And so the answer is pretty easy, and that's going to be the model with all of the predictors in it, with arm, waist, and height, because it is explaining the highest amount of variability. I also notice that it does have the highest adjusted R-squared as well, which we're going to talk about a little bit more here next. But arm, waist, height. It has the highest R-squared value. It is explaining the most variability, and that's really always the case, that the model with the most predictors, assuming we're looking at the same set of predictors, the model that includes all of them will technically explain the most variability in our particular sample of data. The question is, though, are we concerned about something called overfitting? And that's when, if we keep adding predictors, even if they're bad predictors, to a model, we might just begin modeling what we call the noise instead of the actual signal of that relationship. That we're actually beginning to model our sample observations more than we are the general trend of these predictors with the response. And that's something that we can't really see on a particular sample of data when we do this. And so that's where adjusted R-squared can also come in a little bit, is because it helps us determine how much variability we're probably explaining by random chance each time we add a new predictor. And so that's why adjusted R-squared doesn't go up quite as much when we have more predictors in the model. And so we can kind of see that here, because the second question is, which model do you think is really the best to use? And so at this point, I would say it's kind of a toss-up between this one and this one, where, if we're adjusting for how much correlation we're probably explaining by random chance, now it's a much more pretty even comparison between the model with height and waist versus arm, height, and waist, meaning that we're not really getting anything more out of this model by also including arm length in addition to already having height and waist. And that's probably because arm and height are going to be very or I should say, if it's just those individually, those are very collinear predictors, I imagine. Because I don't know if you know this biologically, but your arm length should be very, very close to your height. They won't be exactly the same, but they'll probably be extremely close. And if we looked at a bunch of people and we look at those two things, they would be very highly correlated variables. So for that reason, it doesn't seem like it matters that much if we include both of them. That including height is probably pretty good. Including arm in addition to that doesn't really get us much farther. Highly correlated. Or we could also just say they're collinear if we want to as well. So I'm going to say the model with height and waist is approximately equal to the model with all three. And we generally like the simpler model. Again, it kind of depends on context. I mentioned on the other page, it's not always the case, because it kind of depends on if that other predictor is kind of hard to collect, then maybe we want the simpler model. This is a case where maybe it doesn't really matter, right? Like I don't think if I can get the other two variables, why wouldn't I be able to get arm length very easily? But perhaps maybe I'm looking at some data where I don't have arm length for everybody. Maybe I have some medical data, and maybe 80% of the people I have waist and height, and maybe I say like for basically 100% I have waist and height, and maybe only for about 80% I also have arm length. So that might be a reason that we don't include arm length if it's not present in as much data. But again, it depends. If I have data for all of them, then it doesn't really matter. If I'm missing some data for arm, or it's just harder to collect for some reason, then I think the simpler model would make a lot of sense here. So, yeah. All right, let's also talk a little bit about interpretation of coefficients, because there is going to be a small change when we're doing multiple linear regression. So you remember in simple regression, we talked about having an intercept term as well as a slope term. And so this intercept term is kind of like an anchor to our model, where it tells us kind of where this model starts, where it intersects the y-axis, where x equals 0. Whereas the slope term is telling us about the relationship between the two variables, how a change in the predictor affects or kind of correlates with a change in the response. And so here's an example that we interpreted before, or something close to it, that if y is sales for a particular week, and x is the price of salmon at this particular store, and this is the relationship, then we see that for every 1 unit increase in price, we see on average 2.9 fewer sales that week in salmon. So we have a very similar looking equation here, except that now we're allowing ourselves to have multiple slope terms for each of the predictors that we're adding to this model, that we're allowing each of these predictors to correlate and thus have a relationship there with the response variable. So when that happens, each of these slope terms is telling us about how a change in this variable correlates with the change in the response when these other values are staying the same, when these other values hold constant. And so for that reason, these slope values can actually change when we add new predictors. So even though this is the slope value that I have for price in response to weekly sales, if I add other predictors, I'm going to expect this coefficient can actually change. It might change a small amount, it might change a really significant amount. And it's going to have to do with how much correlation there might be between the predictors I'm adding themselves. Because even though I'm trying to avoid modeling highly correlated predictors into the same model, I'm still going to have predictors that have at least some correlation, maybe a moderate or low amount of correlation. And when that happens, it does actually affect the relationship between this predictor and the response if this other predictor is holding constant. Let's kind of look at an example here. So let's say that we fit another predictor into this model, and this predictor is going to be, let's see, so we have number of customers for the week, and we have, oh, that's right. So price of salmon is x sub 1, and number of customers for the week is x sub 2, each trying to predict weekly sales in salmon for that week. And so now I notice that for x sub 1, which is the one I've already seen, price of salmon, for every unit increase in price, we expect sales to increase by, it's decrease by 2.5 as this other predictor holds constant, and that would be number of customers. So in other words, if I'm comparing 2 weeks where I had the same number of customers in the store, the only difference being that the price of salmon was $1 higher one week than the other, then this is how much effect I expect to see in weekly sales between those 2 weeks if that's changing and number of customers remains the same. And I feel like ideally I should have said on average in each of these interpretations, and I'm realizing that now. So just pretend like I also have on average in both these places, just to be super accurate what we're saying. So we're expecting this much change on average in the response variable. We're not saying that the change is going to be this value, but that on average, this is the change that we're seeing overall in the observations. Some are a little bit more, some are a little bit less, but this is the average change that we've observed. And now I can also interpret the coefficient for number of customers. So for every 1 unit increase in number of customers, we expect sales to increase by 0.6 as price holds constant. So if I'm looking at 2 weeks of data where the price was the same, but I had one more customer than I did before, I expect to see 0.6 more sales on average per additional customer in the store for that week, which sounds pretty good. So maybe salmon's a pretty hot ticket that a lot of people buy because that seems pretty high. But yeah, that's how we would interpret that coefficient. And that hold constant part is important here, again, because when I'm saying that, I'm recognizing the fact that if I'm just looking at one of these predictors, if, let's say, customers and price are correlated, then that means that for every one additional customer that I see in the store, it might correlate with a change in price. Perhaps I have more customers when I have lower prices. So that means that if I don't control for that other predictor, it means something a little bit different. So when I'm building a regression model where both of them are represented with their own coefficients, then I need to interpret each coefficient as a change in one when the other one is remaining the same. So I'm plugging in the same value for one predictor, then this tells me how much change I expect in the response for every 1 unit increase in this predictor. All right, so we'll stop there.